It's 1944. In a hidden airfield outside Berlin, Japanese observers watch in stunned silence as a sleek silver fighter roars down the runway. Twin turbojets scream to life, lifting the aircraft effortlessly into the sky. The Messerschmitt Me 262, the world's first operational jet fighter, has arrived. Faster, deadlier, and unlike anything they've ever seen, it challenges everything Japan knows about aerial combat. But what did Japan truly think about Germany's revolutionary weapon, and could they ever turn it into their own advantage? Japan's awareness of German jet innovation did not emerge overnight. By early 1944, Japanese technical attachés and intelligence officers were increasingly focused on Messerschmitt's experimental programs. Reports filtered through Tokyo via diplomatic cables, submarine deliveries, and technical liaison personnel, revealing hints of a fighter unlike anything the world had seen. The Me 262 promised speed, firepower, and a radical redesign of aerial combat principles. Commander H.E. Iwaya, a key Japanese naval attaché in Germany, played a pivotal role in relaying intelligence. While precise demonstrations he may have witnessed are not fully documented, he and his colleagues collected detailed observations, schematics, and components, including partial Jumo 004 engine elements. Japanese engineers meticulously analyzed the aircraft's features: swept wings, underwing engine placement, tricycle landing gear, and armament layout. Even incomplete data offered profound insights into jet-powered flight. This intelligence raised a critical question. Could Japan turn these reports into a functional jet fighter? Heated discussions erupted in Tokyo. The Imperial Japanese Navy envisioned immediate applications, particularly as the B-29 threat intensified. The Army, meanwhile, worried about stretching already scarce resources. By mid-1944, Japan's understanding of the Me 262 was sufficient to inspire ambitious domestic projects. The Nakajima Kika and the Army's Ki 201, yet the practical challenges of industrial capacity, materials, and fuel loomed large. Japanese engineers understood that the Me 262 was not simply faster, it represented a paradigm shift. Its jet propulsion, acceleration, and climb performance demanded a re-evaluation of air combat doctrine. Observers noted that conventional fighters, even Japan's finest, were suddenly obsolete in speed and energy management. Yet alongside fascination came apprehension. The Me 262 required materials and precision that Japan struggled to provide in wartime conditions, hinting that adopting such technology would be far from straightforward. When Japanese engineers and pilots first observed the Me 262, reactions blended awe with critical scrutiny. Reports described the aircraft moving with an almost otherworldly speed. While Japan's top fighters, the A6M0 and Ki-84 Hayate, reached maximum speeds near 400 miles per hour, the Me 262 cruised comfortably at 460 miles per hour and could briefly surge to 540 miles per hour. Pilots and engineers alike recognized the strategic implications immediately. The Me 262 could ascend at nearly 4,000 feet per minute, almost twice the rate of Japan's best interceptors. For a nation under relentless B-29 bombing, this vertical advantage offered hope. Observers calculated that speed and climb could allow interceptors to dictate engagement terms, striking bombers and retreating before defenders could respond. Combat potential went beyond raw numbers. 430mm cannons, mounted in the nose, allowed devastating concentrated firepower. Japanese reports highlighted the tactical flexibility jets could offer: approach with overwhelming speed, attack, then disengage without relying on traditional maneuvering skills. It was a revolutionary concept, challenging Japan's ingrained beliefs about aerial combat. Yet practical concerns emerged. Engine lag made throttle response unpredictable. Takeoffs and landings required long, precise runs, leaving jets vulnerable at low speeds. Several early demonstration flights in Germany reportedly ended with emergency landings due to engine failures, highlighting that raw speed did not guarantee reliability. Fuel consumption and maintenance also loomed as immediate operational challenges. Despite these concerns, the Mi-262 left a lasting impression. For Japanese engineers and pilots, it was a glimpse into the future of warfare, a technology that could transform strategy, tactics, and even industrial priorities if Japan could master it. But it was a reminder that technological brilliance alone could not overcome logistical realities. Analysis of the Mi-262's technical specifications soon tempered initial excitement. The Jumo 004 turbojet was an engineering marvel but notoriously fragile. Lifespans of 10 to 25 hours per engine shocked Japanese engineers accustomed to radials lasting hundreds of hours. Each combat sortie risked depleting a substantial portion of an engine's total operational life. Metallurgical requirements compounded the challenge. High-temperature alloys containing chromium, nickel, and molybdenum were critical for safe jet operation. Japan struggled to source sufficient quantities, forcing engineers to consider substitutions that compromised reliability. Fuel logistics presented another daunting obstacle. The Mi-262 consumed high-octane aviation gasoline at nearly 3 times the rate of conventional fighters, straining Japan's already limited fuel reserves. Even modest deployment plans risked exhausting stocks quickly. Manufacturing the aircraft was equally difficult. Each Mi-262 required roughly 6,400 man-hours to complete, far more than Japan's domestic fighters like the Zero or Kai-84. Operational limitations further undermined the Mi-262's appeal. Engine sensitivity made rapid maneuvers risky, while takeoffs and landings remained perilous. The aircraft demanded precision and discipline from pilots, skills Japanese aviators could master, but only with significant retraining. These realities forced Japan to confront a critical truth. The Mi-262 was revolutionary, yet it was also deeply dependent on Germany's industrial strength, materials, and production expertise, advantages Japan lacked in late 1944. Despite these obstacles, Japan pursued its own jet program, the Nakajima Kika. Initiated in August 1944, the Kika aimed to apply Mi-262 principles within Japan's industrial constraints. Direct replication proved impossible. Aluminum scarcity led engineers to use steel in major components, while wood and bamboo reinforced secondary structures. The Kika retained the general configuration of the Mi-262, but incorporated design changes for low-speed handling, reflecting Japan's carrier aircraft experience. Engine development presented the most significant hurdle. Japan could not replicate the Jumo 004, so engineers at Ishikawa-jima Heavy Industries created the Ni-20 turbojet, producing 1,047 pounds of thrust versus the Jumo 004's 1,980 pounds. The Ni-20 was less powerful but feasible with domestic resources. Fuel consumption and reliability remained concerns, yet it represented a functional Japanese jet engine for the first time. By late 1944, the first Kika prototype took shape. Progress was slow due to material shortages, Allied bombings, and the diversion of experienced pilots to conventional operations. The program embodied the tension between Japan's desire to innovate and the harsh limitations imposed by wartime reality. The Kika's story illustrates how ambition and necessity drove Japanese engineers to adapt foreign technology creatively, even when resource scarcity threatened to make the program impractical. By 1944, Japan faced an increasingly desperate war situation. The United States was bombing the home islands with B-29 superfortresses, and conventional Japanese fighters were struggling to intercept them. In this context, the Me-262 sparked intense strategic debates within the Japanese military. Was jet technology a potential game-changer, or merely an impractical luxury that could drain already scarce resources? The Imperial Japanese Navy, led by Admiral Suemu Toyoda, believed jets offered a last hope to regain air superiority. Even a limited number of jet fighters could threaten bomber formations in ways propeller-driven aircraft could not. The Navy advocated for accelerated development of the Kikka, emphasizing operational deployment over perfect performance. They saw jets as a way to offset the increasingly overwhelming numerical and technological superiority of Allied air forces. The Army Air Force, on the other hand, was far more cautious. General Kawabe Masakazu and his staff argued that experimental programs, while impressive, could not justify diverting scarce materials and skilled labor. Producing one experimental jet could consume the resources needed for 3 conventional interceptors, which could be deployed immediately to defend key industrial regions. Army planners also noted the Me-262's operational limitations, maintenance challenges, short engine lifespans, and vulnerability during takeoff and landing, all of which would magnify losses if Japan attempted mass deployment. Engineering leadership found themselves trapped between these competing priorities. Nakajima chief designer Hidemasa Kimura recognized the potential of jets, but warned that Japan's industrial infrastructure was inadequate to meet the demands of a sustained jet program. Even a technically successful Kikka would likely produce too few aircraft, too late to have a meaningful impact on the war's outcome. Worsening the debate was intelligence from Germany. Reports indicated that, despite the Me-262's revolutionary design, German production numbers were disappointingly low and operational losses mounted due to inexperienced pilots and mechanical failures. Japan began to question whether the Me-262 truly represented a decisive weapon, or if it was, in the end, an impressive but strategically overhyped innovation. These strategic debates revealed a broader truth. Revolutionary technology alone cannot guarantee victory. Japan's leaders had to balance ambition with pragmatism, weighing the allure of a wonder weapon against the harsh realities of limited industrial capacity, scarce resources, and the pressing need to defend the homeland. Japan's view of the Me-262 reflected its unique cultural and military perspective. Japanese aviation valued pilot skill, maneuverability, and fighting spirit. Early successes, like the Zero, proved that careful training and tactical ingenuity could overcome technological gaps. The Me-262 challenged this philosophy. Jets relied on speed, energy management, and precision rather than dogfighting skill. Pilots trained for intricate maneuvers faced machines demanding a completely new approach. Hit-and-run tactics felt impersonal, dependent more on performance than pilot intuition. Training concerns added weight. Conventional fighters allowed pilots to develop a close connection with their aircraft. Jets, with delayed throttle response and high speed, compressed decision-making, making pilots feel less in control. Leaders worried this could weaken morale and fighting spirit. Cultural attitudes also shaped engineering choices. Japanese designs emphasized safety and pilot familiarity over maximum speed or armament. This philosophy influenced both the Kikka and post-war jets, prioritizing predictability and handling. The Me-262 forced reflection on tradition versus innovation. Could Japan adopt revolutionary technology without losing qualities that had made its air forces effective? Some feared reliance on machines could reduce discipline and skill. Others saw jets as a way to extend traditional warrior values into the modern era. Ultimately, Japan judged jets not just on speed and firepower, but on compatibility with training, human factors, and military ethos. The Me-262's impact on Japan went far beyond the war. Japan never fielded jets in large numbers, but studying German designs and building the Kicker gave engineers valuable knowledge of turbojets, high-speed aerodynamics, and the interaction between engine, airframe, and pilot. After the war, these engineers joined Japan's emerging aerospace industry. Their experience helped evaluate foreign aircraft, develop training programs, and design new planes. Methods used to study the Me-262, careful observation, documentation, and practical evaluation, became standard practice in post-war aerospace research. Operational lessons were crucial. The Me-262 highlighted engine reliability, fuel efficiency, and maintenance planning. These lessons influenced Japan's post-war procurement, including the F-86 Sabre. Engineers prioritized dependable, maintainable aircraft over purely theoretical performance. Manufacturing philosophies evolved too. Companies like Mitsubishi and Kawasaki developed quality control, testing, and resource-efficient production, addressing challenges seen with early jets. This approach later benefited both military and commercial aviation. The Me-262 also taught a broader lesson. Technology is a system, not isolated parts. Engine design, fuel, pilot training, and production are interconnected. Post-war programs adopted this systems thinking, applied to fighters, transport aircraft, and even space research. In the end, the Me-262 shaped Japan's approach to innovation. It showed that revolutionary ideas need industrial capability, strategic planning, and practical implementation. This philosophy, born from wartime necessity, still guides Japanese aerospace thinking, balancing ambition with reliability and innovation with pragmatism. The Me-262 meant different things to different nations. For Germany, it was a final hope. For the Allies, a glimpse of the future. For Japan, a window into possibilities tempered by industrial reality and cultural perspective. Today, Japan's assessment reminds us that technology alone does not win wars. Wisdom, infrastructure, and skill are equally vital.